This is Euclid's proposition 4, also known as the side-angle-side congruence theorem. So proposition 4, or side-angle-side congruence, states that if two triangles have the two sides equal to two sides respectively, and have the angles contained by the equal straight lines equal, they will also have the base equal to the base, the triangle will be equal to the triangle, and the remaining angles will be equal to the remaining angles respectively, namely those which the equal angles subtend. Now, basically that's a really long and somewhat complicated way of saying that if you have two triangles, and they both have two sides, and the angle between those two sides are equal, then the two triangles are congruent. It teaches us how to prove this, that if they have two equal sides and one equal angle, you can superimpose one triangle on another, line up the initial vertices, and determine the coinciding sides and bases so that you can prove mathematically the congruency of the triangles. So the principles of this are superimposing triangle A, B, C so that point A is directly on point D. So because of a few different things, this works. First of all, the common notion for things that coincide with one another are equal to one another is a lot of the underpinning of why this works logically. So the coincidence of vertices, because line AB here, this line coincides with line DE, also the same line, point B coincides with point E, which we can see. The coincidence of sides, because angle BAC coincides with angle EDF, those are the same, then line AC, line A to C here, coincides with line DF. D to F is again the same line, and point C coincides with point F, as you can see down here. Coincidence of bases, because point B here, again, coincides with point E, point C coincides with point F, then line BC coincides with line EF. It's kind of a long way of saying that if you take two triangles that are equal to each other, in order for them to be proven equal, you just have to put them on top, and they all have to line up perfectly. So in the real world, Euclid's proposition 4 can be seen in a number of different things, including the Warren truss. It's also known as the equilateral truss, and it's a truss design that's based on equilateral triangles, and it was patented in 1848. It's used on everything from bridges to biplanes, and a truss is a structural support used to save weight and redistribute it. So as you can see, it's useful here for a bridge to help suspend the bridge over this railway track. It's also useful to help support the two parts of the wings of a biplane. So the triangle is the only polygon whose shape can't change without changing the length of a side. So a support made of a triangle, it can't deform when it's put under load. If there's any stress put on it, it can't reshape, it can't collapse without changing the shape of a member. So there's no way for it to fall apart under stress. And so they're used a lot in structural engineering, dating even back to the Romans. Now, Euclid's proposition 4 is proof of why the triangle is unique amongst polygons, showing that a triangle's congruence is fixed by its sides and an internal angle. If these triangles on this bridge here weren't equal and could collapse, then the whole bridge would fail the second it's put under load.